Hello again. Here is question 20, a probability question. You've got 5 $2 coins and 2 $1, so 7 coins altogether. Pick 3 coins at random. What is the probability that I put out exactly 5? Well, with 3 coins, to get your 5, that would have to be a 2 and a 2 and a 1. That's the only way to get it with 3 coins, 2s and 1s. So this you have to recognize as a hypergeometric problem where we're required to get exactly 2 of the 2s, and then the other one will necessarily be a 1 of the 3 we're choosing. Having recognized that, which is probably the hard bit here, we now just have to go along and just fill in with the numbers. So we've got that our total population N is we've got 7 coins altogether. D, our number of successful ones that we're interested in, well, there's 5 of the $2 coins. I'm going to concentrate on getting the 2 2s, but you could concentrate on getting 1 1 just as well. Anyway, I'm concentrating on the 2s, so there's 5 of them. N is our sample size, which is 3, because we have to get 3 coins out. And X, the number into it, we must get exactly 2 2s. So those are our numbers that we then have to put in to the equation. The equation being that the probability that X equals X equals dC X N minus dC N minus X and NC N on the bottom. Okay, we just now have to fill in the numbers here, and that should give us D is 5, C 2, minus D is 2C1, and we've got 7, and we're getting 3 of them. Okay, and we will now replace all our C's. That's the probability that we have exactly 2 of the $2 coins. Replace that with all factorials, so that's 5 factorial over 3 factorial 2 factorial times by 2 factorial over 1 factorial 1 factorial, and that's 7 factorial over 4 factorial 3 factorial, which we should then, it says there's no need to simplify your answer, so I imagine that if we were to stop there, that would be just fine, but these don't look too unpleasant. They're all pretty small numbers. I might just keep going with that. 5 factorial divided by 3 factorial leaves you 5 times 4, and there's still a 2 on the bottom. That's the first one. Now 2 factorial over the 1s, well, that's just going to be 2. And 7 factorial divided by 4 factorial leaves you 7 times 6 times 5, and that's all divided by 3 factorial. Okay, let's just do some dividing out. 2 goes into 2, 3 2s are 6, goes into 6, so that lot equals 4 times 5 over 7 times 5. 5's divide out, and we're left with 4/7, which will be the answer. Now, all that was reasonably straightforward once you had recognized that this was a hypergeometric situation. If you didn't recognize that, it's possible to do this a different way. Now, I won't go through it all, but you could use a tree diagram where that's the probability of the first coin, then the second, and then the third. Now, this is a situation of not replacement, so the probabilities would change to go along, so you can get a 2 or a 1, 2 or a 1, 2 or a 1, you know, coins each time. The probability of getting a 2 to start with would have been 5 out of 7. Then if the first one you got was a 2, there's now 4 left, and there's only 6 left there. And then if you got a 2 the second time as well, if you get a third one, it would be 3 out of 5. So the probabilities change down each of the legs of your tree diagram, and then you could find your successful ones and work it out. anyway, you could have done it that way if you hadn't recognised that this was the hypergeometric situation. That looks like would be much the easiest way to do it. Okay, that's that.